Hi, this is Yufan from Purdue University, and today I'm going to share some recent development on the single-source shortest path problem, and this is a joint work with Peter Jin and Ken Kwangru. The problem definition is that you are given a directed graph with real number edge weights, and you need to compute the shortest path from a given source S to each other vertex. And if there is a negative cycle, then you need to output one. There has been tons of research on this problem. Without any constraint on the graph, Bellman-Ford was the best algorithm. And if we know the graph is non-negative, then Dijkstra is much faster. There was a recent breakthrough which improved Dijkstra on the sparse graphs. An important special case is the graph has integer edge weights. There are many efficient algorithms for this case. One is based on mean cost flow, and another is based on low diameter decomposition. And the one based on low diameter decomposition can give you a nearly linear running time algorithm. About 2 years ago, Jeremy Feynman came up with this amazing algorithm, which is faster than Bellman-Ford. So this is the first algorithm which is faster than dynamic program. The runtime was later improved to m times n to the power of 0.8. And in this paper, we gave another algorithm. The runtime depends on the edge density. So if the graph is dense, the runtime is the left part. And if the graph is sparse, the runtime is the right part. There are two recent exciting papers which further push down the running time. Check them out if you are interested. So, in this talk, we assume that after some pre-processing, each vertex has a bounded degree, big O m over n. And through this talk, we focus on the dense case. So you can imagine m is roughly n squared. We call a vertex is a negative vertex if it has outgoing negative edges. And in any visual example, we use red to denote negative vertices and negative edges. So as we have seen in the literature, if the graph is non-negative, the problem becomes much easier. So a natural question is, can we turn the input graph non-negative without destroying the underlying shortest path solutions? In 1970s, Johnson gave such a tool called price function. So basically a price function phi will assign a real number onto each vertex. And afterwards, each edge uv will be reweighted by adding the quantity phi u minus phi v, as shown in the example below. So how does this help? So let's consider a graph with one negative edge. If we apply this blue price function, then this graph will be turned non-negative. So we can see the leftmost edge will be added by the quantity 5, basically 3 minus negative 2. So now we know price function can help us turn graph non-negative. But does it destroy the underlying shortest path solutions? So let's consider one ST path. After we applying the price function, the edge weights are changed by these quantities. And we see all the intermediate terms, they cancel out. So the length change of the whole path is, in the end, turns out to be like phi s minus phi t. So this implies for any two ST paths, their weight change is the same, so the shortest ST path will be preserved. So price functions doesn't destroy shortest path solutions. But is there a universal price function which can help us turn all negative edges non-negative? In Johnson's paper, he gave such a price function. Basically, in the input graph G, you add a super source, S star, and From S star, you add length 0 edges to each vertex. Then the price on vertex V is the distance from S star to the vertex V, and this can reweight all edges non-negative. The proof is simple. So we know that after reweighting, the length of UV becomes this quantity, and this is closely related to the triangle inequality for distance. So we know the distance from S star to V is at most the distance from A star to U plus the length of UV, because the left-hand side is the shortest path and the right-hand side is just one path from A star to V. So after rearranging, we know the reweighted length of UV becomes non-negative, and this holds for every UV. But the problem is that computing this price function requires solving another single source shortest path problem. So if you naively apply this price function, it won't make the problem easier. You need to utilize some graph structures. How can we compute price functions? We need some tool called hop distance. One H hop path is a walk with at most H negative edges. So in this graph, this path is a 2-hop path, and this path is a 1-hop path. We can define H hop distance as the length of the shortest H hop walk from S to T. And this distance can be computed in O tilde H times M time by combining Bellman-Ford and Dijkstra. So basically the running time is the number of hops times the size of the graph. Now let's move on to talk about the framework we are going to use. We follow the framework proposed by Feynman. So instead of reweight negative edges, non-negative all at once, we are trying to make progress iteration by iteration. So in each iteration, we will find a set of negative vertices, S, and their corresponding negative edges. And we hope S has some special structure we can utilize later. Then we focus on the subgraph induced by S. So the set of negative edges corresponding to S plus all the non-negative edges. By exploring the graph structure in this subgraph, we can compute Johnson's price function quite efficiently and make all negative edges in it non-negative. Then, in next iteration, we will work on the reweighted graph. In this way, the number of negative edges are iteratively decreased, and in the end, there will be no negative edges. And we can run Dijkstra on the non-negative graph. So the key challenge of this problem is that, so let's consider a set of negative vertices S and its induced subgraph GS. So if S contains a lot of negative vertices, then we know in this subgraph GS, the shortest path can in principle contains a lot of negative edges, right? So to compute the shortest path distance, we need to compute a large hop distance, like the size of S hop distance. This can give us Johnson's price function, but this will take us O tilde M times the size of S time. So on average, you are paying O tilde M per negative edge, and this is the bottleneck of the whole problem. To overcome this issue, Feynman came up with this idea called hop reduction. So basically, he wants to build one auxiliary graph edge such that any L hop walk in the input graph G is equivalent to one L over H hop walk in the auxiliary graph edge. Or intuitively, you can imagine it as the H hop distance in the input graph is roughly the 1 hop distance in the auxiliary graph edge. And for convenience, we will call this edge an H hop reducer for G. So how does this help? So let's say we can build some small size hop reducer for G. Then instead of computing distance in G directly, we can work in the hop reducer edge. And because it has small size and the hop count is reduced, we can compute the distance efficiently. So how can we build hop reducers? Let's look at a naive construction. So I will copy the input graph G h times. Here in the example, I let h be 3. Within each layer, I will keep all the non-negative edges. And between consecutive layers, I will add these pointing forward negative edges. Also, to prevent a walk getting stuck in the final layer, I will add these length 0 self-loops between consecutive layers for each vertex. And this also makes the proof much easier. So now we can simulate a walk in G in the hop reducer we just built. Let's look at a walk. If we are going through one negative edge, then we jump to the next layer in the hop reducer. And we can keep moving. So when we arrive at the final layer, we first use the length 0 self-loops to jump back to the first layer, then keep moving. In this way, we can simulate any walk in G in the hop reducer. But how is hop reduction achieved? As we can see, this walk still contains 3 negative edges, in other words, 3 hops. It turns out we can find some simple price function to reweight all these pointing forward negative edges non-negative. Basically, you will add a big constant to these pointing forward negative edges. And this won't affect these non-negative edges within each layer. The only downside is that all these wrapping around self-loops, they can become negative. This is another price function that works. Now we have achieved the hop reduction. So is the problem done? It turns out because the hop reducer we construct is too large, so in the end, computing the L hop distance still takes you L times m time, because the hop reduction you achieved is cancelled out by the graph size inflation. So Feynman found that we have to utilize some graph structures. And one special structure he focused on is called h-remote sets. So basically, we call one vertex S can negatively reach another vertex T in h hops if the h hop distance from S to T is negative. And we can define the h hop negative reach of vertex S accordingly. So basically, it's the set of vertices where it can negatively reach in h hops. And for a vertex set capital S, its h hop negative reach is basically the union of the h hop negative reach of all vertices inside capital S. And we say such a set is h remote if its h hop negative reach is relatively small, quantitatively smaller than n over h. So intuitively, this means this set of negative vertices are very far from the rest of the graph. So how does this help to reduce the size of the hop reducer? So again, we can build the layer graph and achieve hop reduction. But this time, let's look at these vertices outside the h hop negative reach of S. So I claim the prices on these vertices are all 0. The intuition is that these vertices are very far from these negative edges. So the distance from the supersource A star to them can only be 0. This distance cannot be negative. So this implies all these length 0 self-loops between consecutive layers, they remain length 0. And we can actually compress these parts, or equivalently, when we build the layer graph, we only need to copy the h-hop negative reach of S multiple times. And we know this h-hop negative reach has a small size by the definition of h-remote set. So this hop reducer turns out to have a small size. It has size big O M. And computing Johnson's price function, or equivalently distance, is much faster in this hop reducer because the hop reducer has size roughly big O M, and you only have to compute the size of S over H hop distance in this hop reducer. Okay, that's super good. However, it turns out it's quite expensive to find these good structures, in other words, like H-remote sets. So in this paper, we instead consider the following structure called weakly H-remote sets. They are sets of negative vertices with eta hop negative reach at most n times eta over H for all eta. Let's take a look how these weakly remote sets look like. This is one weakly remote set S, and we define Gi to be the subgraph induced by the 2 to the power of I hop negative reach of S. So by this definition, we know the one hop negative reach of S has at most n over H vertices. So in other words, G0 has at most n over H vertices. Because of the degree constraint, we know G0 has at most m over H edges. And for G1, we know it has at most 2n over H vertices and 2m over H edges. The similar property holds for any I. And if I equals to log h minus 1, then we know G log h minus 1 has at most n over 2 vertices and m over 2 edges. And for G log h, we know it has at most n vertices and m edges. So basically, the h-hop negative reach doesn't have any size constraint. This also shows this structure is weaker than H-remote sets. And we can imagine like G log H is basically the original graph G. The good news is that this weaker structure is much faster to find. It only takes you O tilde m times H time. But the challenge is that it's unclear how this structure can be useful for building hop reducers. Maybe let's start with the simplest idea. We again build this compressed layer graph. So we copy the H over 2 hop negative reach multiple times. And we can achieve the hop reduction. But the problem is that this hop reducer is pretty large because we have no size constraint on the H over 2 hop negative reach. So how can we deal with this problem? Let's come down and see if we can find any structure in this hop reducer. So let's consider any walk from the first layer to the last layer. We can see it's actually one H over 2 hop walk in G log H minus 1. It's in a smaller graph. And it's from the tail of one negative edge to the head of another negative edge. So maybe we can skip building out these intermediate layers. Instead, we adding these all-to-all shortcuts between all the negative vertex pair with length equals to the H over 2 hop distance in the smaller graph G log H minus 1. Because the original graph is pretty dense, the number of shortcuts we added is shadowed by the number of edges in the original graph. So the size of this hop reducer is much smaller, it's only big O n. So now we overcome the issue that the hop reducer is too large. So to compute Johnson's price function, we need to compute the distance in the original graph G, which is G log h. Then to efficiently compute this distance, we need to build some hop reducer with small size. To build this small size hop reducer, we need to add these shortcuts. So it requires us to know the distance in a smaller graph, G log h minus 1. And to compute this distance, we again need a small hop reducer in the smaller graph. And you see the pattern. So here comes the core idea of this paper. We want to bootstrap the construction of these hop reducers. And the base case is that we can build a one hop reducer for the innermost graph, G1. It's simply G1 itself. Now assume we have the hop reducer hi for Gi. We want to build the hop reducer hi plus 1 for Gi plus 1. How can we do that? We simply adopt one similar construction, so we shortcut the layer graph. The size of this graph is dominated by the size of Gi plus 1, so the left-hand side. And to construct this hop reducer, we need to know the distance from each negative vertex in the graph Gi. So if we utilize the hop reducer hi, the problem is reduced to computing two hop distance for each negative vertex in hi. So overall, it takes the number of negative vertices inside S times the size of hi, which is roughly the size of Gi. So now we know it takes this much time to build the hop reducer hi plus 1. So the overall running time will be dominated by building the hop reducer h log h. So it takes the number of negative vertices inside S times the size of graph M. So we can find this runtime turns out to be too slow. You are still paying big O M per negative edge. It's far from our goal, like big O M over H per negative edge. So how can we deal with this issue? The bottleneck is that we have to compute this all-to-all shortcuts between all negative vertices. This is quite expensive because you need to compute a single source shortest path from each negative vertex. So instead, we can try to sample a set of negative vertices S0 so that it can hit all these paths with a lot of negative edges. So if a path contains a lot of negative edges, then with high probability, one of them will be sampled. Then we only need to compute distance from S0. So now the runtime is the size of S0 times M. If we pick the size of S0 properly, then we get the desired running time. So now let me conclude the talk with a comparison between remote sets and weakly remote sets. So the time to find weakly remote sets is much faster. It only costs you m times h time. And you will find a slightly smaller set. It takes you more time to build hop reducer for weakly remote sets. But we can shadow that running time into the time to reweight all negative edges using this hop reducer. So if you balance the time to find this structure with the time to neutralize all the negative edges in this structure, we get the optimal edge. And this is the overall running time. Basically, it takes m over h time to reweight one negative edge, non-negative, and with some preprocessing, there are at most n negative edges instead of m. Okay, that's all. Thank you.